On the last video, the answer in the book is wrong. I just noticed that, and I double checked it, but they make mistakes, so or typos, and so it just always bothers me. I always like to point it out to students so they know, yeah, the book was wrong on that one. So it wasn't me this time. I mean, I make plenty of mistakes, but okay. Now we're going to talk about multiplying with negative radicands. Now, in the past we had a property that the square root of a times the square root of b is equal to the square root of ab. But this is only if the square root of a and the square root of b are real numbers. Okay, now in the past we didn't deal with any imaginary numbers because we didn't know about them, and so it didn't really come into play. But now sometimes students think that they can use this rule, but that rule only applies for real numbers. Okay, so the product property for radicals is only for real numbers. So what do you do if you don't have real numbers? Okay, so we'll show you. So here it says multiply the square root of negative 49. So right away I'm just going to say the square root of 49i times, I'll just put a dot, and then it says the square root of negative 4. So I'm going to write it the square root of 4i. Now you could do this in one step, but the square root of 49 is 7. So I have 7i times, and the square root of 4 is 2i. Okay, this is multiplication, right? It's all multiplication. 7 times I times 2 times I. All right, 7 times 2 then. You could rearrange it. This might make it easier for you to see what's going on. So you're going to take, the coefficients, the real part, and multiply those together, and then you're going to multiply the i's together. So you get 14i squared, but I told you that we're never going to have an exponent higher than 1 on I. So we have to replace that I squared with a negative 1. So you're going to have 14 times negative 1, which is going to be negative 14. Now that's the answer. It's a real number, but all real numbers are complex numbers. Okay, so I don't know if we mentioned it before, but when we multiplied complex numbers, we always got another complex number. Okay.